Now in section 4.3, we will be learning how to use a very useful linear algebra library called eigen. You might have studied linear algebra before and thought, wow, I'm never going to use this thing. I remember when I studied myself in college, I left that class very confused. But in fact, linear algebra is incredibly powerful and incredibly useful in robotics. And there's a great text in a great class by a professor called Gilbert Strang from MIT. I benefit greatly from studying his course online and also his 4th edition book to Intro to Linear Algebra. I will add a link in a second. Well, eigen is a very powerful library that can often be used in our C++ programs. One thing that happens with ROS messages is that even though they're designed for serialization, that means they're very well packaged in order to stream data over the wire, over the net, it's not easy to work with ROS types to perform linear algebra operations. So what we often end up doing is we convert them to eigentypes. In this section 4.3, we will be learning how to use eigen with ROS. Some of the basic things that we need to do is, number one, modify the cmakelists.txt. And another thing that we need to do is include appropriate header files in the CPP files. Here is an example. Now, if we use the cs catkin simple create package in order to create a package, our cmakelists.txt file will automatically include the necessary lines for us to use eigen. If you do that, like previously working with my minimal nodes, you'll notice that maybe lines 12 to 16 have the following text. So find package, CMake modules required. This line includes specific modules some specific modules that enable eigen to work with CMake. Then a dependency here on eigen 3. And finally, providing paths for eigens include directories and some other eigen definitions that exist in your computer. Okay, and all of these lines are necessary for proper compilation. In the C++ file, we need headers to use eigen. Different headers will provide different functionality. These 4 lines included here provide us with basic functionality into the eigen library. If you want to learn more, please click on this link to see which header files you would need for the operations that interest you. Okay, so the rest of this section is going to be focused on this example eigen plainfit.cpp. We can find this program in our example eigen package. So you can just run rosset on that to open the code. Make sure you open the CPP. Now for this section, I'm not going to be looking at the code directly. I've included all the commands right here on the slide. Okay, so let me give you a motivation of what we're going to do. Imagine that we want to define a 2D plane. So 2D planes are defined by a vector that is normal to the plane. So we're going to be working on creating a normal and then creating points around that normal that would define a plane. So the first thing that we would do in eigen is create a 3x1 double precision vector, and we're going to call that object the normal vector. So this is a 3-dimensional vector. So now for illustrations right now, we will always include this namespace eigen followed by the binary scope operator. If you want to skip including this step and just simplify the typing of the eigentypes, you can say using namespace eigen. Okay, so here by using the type vector 3D, we can automatically create a vector. We call it whatever name you want to call it, normal vec in this case, and then you can provide the values and these parentheses. So as you can see, it's extremely easy to create a vector. Now let's say that we want to make this a unit vector. So what we need to do is divide by its norm, that is the length of the vector. Okay, so eigenvector objects allow us just to call norm on the vector object itself. And so here, if we want to perform a division by the norm, we can also implement this self-division. So look at how powerful eigen is, because we can take the vector object, divide by self, or divide by this norm of the normal vector. Yeah, so a very powerful expression right here. The division operator is defined to scale the components of the vector. So as you know, this vector is three-dimensional. By including the division operator, we're dividing each of those elements in the vector. The same thing would happen by using the multiplication operator. So if we have a vector times a scalar, that scalar would multiply each of the vector elements. Now, we have a vector, right? We want to generate points on the plane. So one of the first things we need to do is construct a pair of axes that are perpendicular to the plane. So here we're going to create two vectors, v1, v2. Whenever we have more than one variable, you can just separate them by a comma. Another thing that we're going to do is we're going to construct a 3x3 matrix. What for? To define a rotation matrix. Now this rotation matrix will be a rotation about the z-axis by 90 degrees. So if you're not very familiar about rotation matrices, go back to study Peter Cork's lessons on 2D or 3D geometry, and you can get an idea of how to create these rotation matrices. So the first thing that we do is create the matrix structure. So here we can just very fast call matrix 3D and provide that object with a name. And we can access each of the elements of the matrix using the row method, and then providing an index for whatever row we want to access. We use this double arrow operator to insert the values for that row and then separate them by commas. Again, very easy to use notation compared to what a regular C++ program would do. And so we can fill out these rows very quickly. A Z rotation is defined by this one on the 3x3 position. That's the pivot. And then zeros elsewhere along the row and the column. And so here we have basically what is a cosine of theta, sine of theta, negative sine of theta, cosine of theta. And that defines the Z rotation. Now if you want to print out this matrix, we can do that with ROS-Info or ROS-Info Stream. I believe this is the first time I showed you ROS-Info Stream. It's similar to ROS-Info, but the difference is that any time that we include this stream suffix right here, this is going to work using cout notation. So you can see here we're going to skip a line using endl, and then we can use this operator and append then the matrix rotation Z. You'll also notice that eigen has really nice formatting here. Okay, so if we want to rotate normal vector, how do we do that? Well, we have a rotation matrix multiplied by the vector. And that's what V1 is going to be. It's going to be that normal vector rotated by rotation C. And we can do dot product computations to see if this is in fact the case. So now dot products can be done in two ways. The first one, we can use the dot methodology, which is a member of every vector object. So here we can say v1 dot operator dot method and then include a new vector. Okay, so here we can save that float result into double dot prod. Another thing that we can do is the inner product, and so that inner product can be this depending how the vector has been defined, but in this case the inner product will also give us one number. So this is here a 1 by 3 and this is a 3 by 1, giving us a 1 by 1. So this is v1 dot transpose times the normal vector. Now the next thing we want to do is create a vector on the plane, and to do this we need to use the cross product. Okay, so here the cross product of v1 cross v would result in a perpendicular vector, giving us that vector on the plane, v2. Okay, if you're losing the visualization here, please go slowly through this code, maybe debug through each of the lines, and then try to plot the images. Once we have this vector on the plane, we can use v1, v2, and normal vector to create many points on that plane using the following equation. Some scalar times v1, this is, and then plus some scalar times v2. This is just a linear combination of vector v1, v2 to get a third vector, and then plus c times normal vector. Now c here is going to be a distance from the origin to the plane, and so we multiply that times our normal vector to get that distance. And so what we want to do is by changing the values of a and b, we're going to get different points. Okay, this is just a linear combination of vectors. Now, how can we change the values of a and b? A really good way to do that is to generate random points. Okay, random points for a and b and themselves generate random points that are on the plane that we desire. So here we're going to store many random points on a matrix. Now here we're not going to use matrix 3 as we did before. We're going to use matrix XD type. This means that we need to define the dimensions of that matrix. We'll call that points met, and we're going to say that this is a 3 by some n dimensionality. So this is the XYZ coordinate, and then this is just many points that we're going to be creating. Endpoints is provided by us, and I don't show the value here in the slide, but it's right there in the code. And so basically we would do a for loop over the number of points and then use values that come from a 2 by 1 random vector to include in our equation right here. For example, this is the random vector, and we can use the set random method to provide a size for it. So we're going to say 2 by 1. So every time we go through the for loop, we're going to get a new pair of random numbers. And then in the equation where we're getting points on the plane, we say let's take the first element of that vector, and it's going to be a random number, multiply that by v1, and then let's take the second element of that random vector and multiply that by v2, and then add this third element, which is the distance times the normal vector. And so every time we go through the for loop over the number of points that we want to create, then we're going to get a different point on the plane. Now, to make things more interesting, we don't want to just have all those points on the plane. We want to vary a little bit their position. So something we're going to do now is introduce random noise. That noise will vary from negative 0.1 to 0.1. And we're going to create a matrix that is going to be three-dimensional, and also will have the same number of columns as our points over here, which is n points. So this noise will be included both in the x, the y, and the z. So we're going to get a little bit of scattering both vertically, horizontally, and transversely to make that a little bit more interesting. So we can very easily create a matrix, 3D matrix with random noise by calling random yes, this random class on matrix XD and providing the dimensions that we want to create. So this is a fantastic way of very quickly generating noise. And so then we can just take that points mat and add the additive noise. Now here the noise gain will be input by the user, and that's what's going to actually allow us to scale this to 0.1. So far what we have now is a set of column vectors that lie approximately on a plane. And they're all some distance dist from the origin, and they have a surface normal called normal vec. The next thing that we want to discover that's most interesting is to say, let's discover what the original plane is using only the data. So of course we just constructed that, but now we just want to look at the data and say, what is that plane? What is the surface normal to that plane? And this goal or this example is going to be very useful in point cloud processing operations. When you're using point clouds in a robot, which is very common, oftentimes you will be interested in computing flat surfaces. For example, you want to know where the floor is, or you want to know where the roof is, or you may know where a wall is located, or a door. And all of these are surfaces or planes that can be approximated by using linear algebra on the point clouds. So what are we going to do next? How are we going to discover such a plane? Well, the first thing we're going to do is compute a centroid of all the points that we have in our data. And then we're going to take those points and subtract the centroid from them. And the next thing we want to do is get a covariance matrix. So covariance matrices are symmetrical, and so that means they have the same number of rows as number of columns. One way that we can do this is by multiplying our rectangular matrix by its transpose. So we'll have a 3 by n points and multiply it by n points times 3. That'll give us the covariance matrix. Okay, that covariance matrix basically is telling us information about the variation of data both in the x, the y, and the z directions. Then we can use some techniques related to eigenvalues and eigenvectors on covariance matrices to extract the different directions of the main vector components and that covariance matrix. So if you're not very familiar with this, I'll try to walk you through it, or you can read up on a text. So let's compute the centroid of the data. And to initialize this structure, we're going to have a 3 by 1 matrix, and it could be a vector, but here we're going to call it a matrix. And look at how we can use this method 0 just to initialize everything to 0 very quickly. Then we are going to sum across the column vectors of points mat using a for loop. And later on, we'll divide each part by the number of points. So again, it's very easy to access the values of the columns of a matrix. We can use this call method, provide an index that here comes from the for loop, and then use this addition operation on centroid itself to accumulate the values across the columns. Once we have the centroid, what we want to do now is subtract it from each of the points. So imagine the centroid is, say, 1, 1, 1. By subtracting each point from 1, 1, 1, it basically is shifting the whole point cloud to a location 0, 0, 0, and facilitate then the covariance matrix computation. Okay, so the first thing we do is we're going to copy our matrix to another variable called points offset matrix, or mat. And so here we can just do an equal sign like this, which is very convenient. Then we run our for loop, and we can just subtract the centroid from each of the points or each of the columns. Okay. And the covariance matrix is going to be generated by multiplying our matrix structure by its own transpose. Here you can notice how can we call it transpose? Well, all matrix objects have this built-in method, transpose, so we can just call it in this way, and we can multiply two matrices using the matrix operator. So this is going to be stored in a 3D matrix that we're going to call covar or covariance. One of the nice functionalities of eigen is to compute eigenvectors and eigenvalues. In this 3D plane that we have, the direction of the smallest variance is going to be the one that corresponds to the vector normal to the plane. So here what we're seeing is that we have big variations along the x and the y direction. Think about that plane. It's going to span a lot of space on the xy plane. But when it comes to the z plane, we just have a little bit of noise. Almost everything is on the same surface. So when we compute the eigenvectors, the smallest eigenvector is going to be the one that represents a vector that is normal to the plane. Okay, and eigen provides a special eigenvector eigenvalue solver object. In order to initialize this object, which is here eigensolver, we provide the type of the structure that we want to resolve the eigenvectors and eigenvalues from. And then we have our object name, and we pass as an input to the constructor the name of the variable that we're working with. Okay? So once we have this eigensolver object, we can extract the eigenvalues and the eigenvectors. Here we're going to save the results of the real part of the eigenvalues in a vector called evals. So here we create evals and make this a vector xt. Okay, so no previous dimensionality is defined for this vector. And then from our eigensolver object, we can, in this case, solve for eigenvalues and then extract only the real part. Eigenvalues often will have a real part and an imaginary part. That depends on the structure of the covariance matrix. In fact, in our problem, the covariance matrix is symmetric and positive semi-definite. So there should be no complex part in this covariance matrix, but just for you to understand how to extract the real portion of an eigenvalue, you can call this structure right here. And then the next task would be to search for the smallest eigenvalue and then select the corresponding eigenvector. Here, as I mentioned before, the direction of the smallest variance will be the one that is perpendicular to the best fit plane. Now imagine that we have an IVEC index going through a for loop, and that happens to be the smallest number. Look at the code for the details. Then we could say, let's take the eigensolver object, then take the eigenvector, and take the column with this IVEC index, and again the real part, extract all of that, and then that would give us the indices for the normal plane. So here, the next thing that we're concerned with is to compute the distance of the plane from the origin. And one way to do that is by using projections. We want to project the vector that goes from the origin to the centroid onto the normal plane. If you don't remember too much about projections, we can achieve them through dot products. So imagine we have the projection of the vector 1, 2 onto the x-axis. How do we do that? So we would take the 1, 2 vector, the column vector, and then do the dot product with the x-axis, which would be 1, 0. And when we do that, then we just keep the part that is on the x-axis. This 2 goes away because it's on the y-axis, and we just keep this 1 over here. So that would be a projection of 1, 0. Or if this vector was a 2, 2, then the projection would be a 2, 0. So that's an easy way. If you have a reference axis, the x-axis, or in our case here, the vector normal to the plane, you can project against that and then keep just the distance here from the plane to the origin. And so we can do that very easily by taking our vector estimated plane normal and call the dot method on it, and then pass the other vector that we want to do the dot product with. And that distance can be saved right here. Here's an illustration of what a projection looks like. You might have some blue vector like this, and you want to project onto this vector. So you just basically keep the component along that plane. Okay, so this is a very quick run through section 4.3, examining eigen functionality. Incredibly powerful, easy to use library. Of course, you need to spend some time learning its API, but you will find it to be very useful in all robotics work whenever you need linear algebra. And one more structure I would like to visit with you guys. It is not part of our C++ code, but it's also very important, is something called the eigen-affine transformation. The eigen-affine 3D is another object of the eigen library that serves as a coordinate transform operator. You can think of it as a homogeneous transformation. So let's say that you have a Ross TF transform, and we want to then put it into a eigen-affine object. We want to do this because then we can use the affine object easily to do transformations later on. So how would we copy the TF transform into the affine object? Well, we would do that by parts. The first thing we would do is fill out the point information. The point information is located on the fourth column of the TF transform. Once we do that, we want to fill the rotation matrix, which is a 3x3 structure on the upper left corner of the TF transform. And finally, we would want to fill out the bottom row, which is characteristically 0001 in our homogeneous transformation. So here we can have, for example, a definition of a function called transform TF to eigen. And this would take this TF transform object. We're passing in that by reference. Within this method, we will create an affine 3D object. In this case, we're just going to call that E. And as we mentioned before, the first thing we need to do is copy the point from our TF transform object. If we run a for loop from 0 to 2, 0, 1, 2, then we can say, hey, let's take our affine object and let's work on the fourth column, which is index 3, because we start at 0, so we have 0, 1, 2, 3. And then for rows 0, 1, 2, let's copy that point from the TF transform. We do that by using the dot operator and calling getOrigin, and then that would return the three-dimensional vector. But if we want to access each element, we can append a square bracket and include our index I here to do that copy. On the same loop, we can also extract the rotational part of the matrix. So if we include a second variable j, then what this loop is going to do is going to say, let's start with row 0, and let's go through columns 0, 1, 2. Then let's move to row 1 and go through columns 0, 1, 2, and finally go to row 2 and again go through columns 0, 1, 2. We can use the method getBasis instead of getOrigin on our TF transform object to pull out that rotation matrix, and again we can index that result not just with I, but this time with I and j to extract the right element and then place it into our affine object E dot matrix. And here we need slightly different syntax with I comma j in parentheses. After we've done that, then we can by hand just fill in the last row of our affine transformation with 0, 0, 0, 1. Okay, so we can do one more for loop and then access that third row, the third index, which is our fourth row, and go through columns 0, 1, 2, and setting that equal to 0, and then having the last element, the fourth row, the fourth column, and set that equal to 1. Once you have an affine transformation or an affine object, you can use that to multiply other affine objects for transformations, or even pre or post multiply, or use it to pre-multiply a vector 3D object to transform those points to new coordinates. So for example, let's say there's a point P. This could be maybe the wrist of a robot, okay? Point with respect to sensor, or it could be a sensor. So you can create this vector 3D like this. Okay, then we want to get the transformation from TF to the affine object and eigen. That affine object is going to be called affine sensor with respect to the world. So this is going to be a transformation from the world coordinate then to the sensor. We can quickly now do that by using that definition from our previous slide. Transform TF to eigen and providing the TF transformation. Okay, and then we can take that point, which is with respect to the sensor, multiplied by the transformation of world to sensor, or sensor with respect to world, and create or change the coordinate axes of that point and make that point with respect to the world where it's always more useful. Okay. If we want to change that point in the opposite direction, we can always use an inverse method. So if we want to take that point and convert it with respect to the sensor, not with respect to the world, we can have this P back and sensor frame, take the affine sensor with respect to the world, and simply called the inverse method of that, provide the point, and then get the transformation in the other way. This concludes section 4.3, and again, it's introduced us to very powerful tools that are going to be very, very useful for us later on, working with point cloud processing and also transformations on multiple frames on a robot, camera frames, sensor frames, 4 storage sensors that will help with grasping, and a multitude of tasks.